I'm sure that you've all talked about, and the inefficiency of conversion of the sunlight to liquid fuels is well known. If you think about the ways that we think about the pathways, right, there's feedstock conversion, right? I know there's sessions on that being discussed here today, all the algal approaches and pathways, a lot of things being discussed here today, as well as direct conversion. And so when we said, well, what's APRA-E's place that we might want to play in this, we came up with two things. One was around electrofuels, converting directly, not using a photosynthetic pathway to convert to fuels, as well as could we bypass millions of years of genetics of plants, of developing themselves to be plants first, and say, can we actually make them more oil-like, more suited to be fuel right from the get-go? And so some examples of that, if we look at electrofuels, the idea of converting CO2 with a source of electrons through a non-photosynthetic microbe to the fuel was embraced by several groups. OPX Biotechnologies using a conversion of hydrogen-consuming bacteria directly to fuels. And they have been successful in actually converting their free fatty acid to a final fuel product, and they're continuing to develop that. We also had a very interesting project run by UCLA looking at electrochemically produced formate, and again, that group's continuing to work. Our Petro project, plants engineered to replace oil, a lot of approaches we looked at there. You need to, actually combine your photosynthetic optimization, your metabolic engineering into heritable traits. And the goals in that project were to have yields at 2 times the density of corn today at a cost of less than $3 of gasoline equivalent. And again, to highlight some of the approaches, we had everything in that grouping from oil seeds to grasses to trees to others. And a couple of those projects that are interesting, a Camelina project being run primarily by Danforth with a lot of other partners, looking at all 3 of these aspects. Can you get a higher light capturing efficiency? Can you import algae traits to improve the fixation, as well as getting higher yield from the oil seeds? And again, with the goal of meeting 2 times corn at an acceptable cost. Another interesting one is if you look at the University of Florida's partnership with ArborGen, NREL, and Berkeley, loblolly pine, a very well-known crop, grows through the southeast. It currently produces terpenoid components, about a 7% level in them naturally. They've been harvested since ancient times for making turpentine. But can you actually genetically change these trees to produce 3, 4, 5 times as much terpene and still have a healthy tree? Would significantly change the value as an energy crop. We've got a variety of different projects in this space, including combinations of algae and tobacco, where you could get the oil-producing properties of algae ported into a crop like tobacco that certainly grows on poorer lands, and we have a supply chain. So you can see the breadth of approaches that we've taken in our portfolio at APRA-E. Again, some of these may not work. We will look to assess over each quarter and work with the teams to make sure we're optimizing what we do. But the idea is creating a lot of options. I think we all believe here that liquid fuels are an essential piece of what we need to be doing. We've got a lot of great work going on currently to move the existing products to a place that they can be economically viable and be a significant part of our ecosystem. We need more opportunities to continue to think about improving these things. And so, I'd urge you, any of you who are interested in the space, look at what we've got on our website and chat with these teams, because I think there's opportunity as you're looking to move the technologies forward when new partnerships could arise.